Welcome to P. Clark Calc, Practical Calculus for the Busy Math Student. And in this video we're going to take a look at the integral test for convergence, which is used in Calculus 2. We're trying to determine whether infinite series is convergent or not. So let's see how that's done. Here we're looking at infinite series n times e to the negative n over 2, and we're trying to determine if this thing is convergent or divergent. And the test that we're going to use to prove that is the integral test, which basically states that if you have an infinite series, you define the corresponding continuous function. Remember, n is an integer, a natural number, but when we convert that over into the x variable, then we have a continuous function, and that means we can run an integral on it. So we basically run the corresponding improper integral, f of x dx, on the same bound. We have 1 as the lower bound here. It does not have to be 1, but whatever it is for the series, we would use the same lower bound for the integral, and that would not affect qualitatively whether that converges or diverges. But basically what the integral test says is you run the improper integral and determine if that is convergent or divergent, and then the infinite series must have the same behavior ultimately. So that's what we're going to do here. It's really the only good option for this particular case. So we start by defining the improper integral. So we're going to integrate from 1 to infinity, x e to the negative x over 2 dx. And at this point in your calculus life, we tend to kind of abandon the formal limit notation when we're doing improper integrals. We understand the infinity symbol is not a number, it's a limit. We're describing what's happening here as x approaches infinity. But we look at the integral and hopefully can determine that is integration by parts. So this is an integration by parts where u is equal to x, dv is the exponential in this case, e to the negative x over 2. So we do our little calculus here in our integration by parts. So du is 1 dx, and then v is going to be negative 2 e to the negative x over 2. So we go ahead and run an integration by parts formula. uv, says we're going to write that as negative 2x e to the negative x over 2 minus the integral of v times du. Now typically the coefficient's almost never useful inside the integral, so we'll write that outside, which is going to make this plus 2 times the integral e to the negative x over 2 dx. You can carry the bounds if you wish. I mean, in integration by parts, sometimes we table the bounds and then just don't forget about them to the end. But that's our integration by parts, and that gets us to kind of the terminal case here. We can integrate that a little e to the kx here. So ultimately our antiderivative is negative 2x e to the negative x over 2. And then this is going to be minus 4 e to the negative x over 2 on our bounds from 1 to infinity. So when we plug, we'd call it plugging the infinity in. That technically is not possible. It's not a number. But we say, well, as x is going to infinity, what is e to the negative x over 2 doing? And in this case, if you look at our first term, we have a little bit of a dilemma. I mean, if you go back to the indeterminate limit rules here, I would have an infinity times 0 case on the first one. The second one is definitely going to 0. And I mean, we could break off and do a L'Hopital's rule and play around with that, rewrite it. However, ultimately in the magnitude game, the exponential factor is going to win that game. And it's been proven. So the e to the negative x over 2 is going to call the end behavior of that term as x goes to infinity. So that will in fact go to 0. So that means our upper bound then is going to be a value of 0 ultimately. And then on the lower bound, we put x equals 1 in there. We get negative 2 e to the negative 1/2 minus 4 e to the negative 1/2. So ultimately those are like terms, and we have a negative sign out front. So we get a numeric value here, 6e to the negative 1/2, which is proof of convergence. If we get a real number out of our improper integral, we call that the convergent case. And then the integral test says, well, if my improper integral was convergent, I can reflect that back up to the original infinite series, and that must be convergent too. Now you have to be a little careful in the convergent cases, because what we've done here, we do have the value of the improper integral. This is not the value of the infinite series. They're closely related, as we find out. However, we're not looking necessarily here to get an actual number for this infinite series. We're not trying to find the exact sum of it. Sometimes that can be incredibly difficult, but we're just trying to determine qualitatively convergent or divergent. So when you see that number on the improper integral, don't read too much into it. When you go back to your infinite series, we're just trying to state, okay, this is convergent or this is divergent. So the integral test here proves, with the low integration by parts, that the infinite series n e to the negative n over 2 is a convergent case. Here at P. Clark Calc, we do practical calculus for the busy math student. But if you'd like to learn more about the integral test or infinite series or calculus in general, you can find them in my calculus books, available for a nice price on Amazon. Until next time, I'm P. Clark.